There are always things that one does not like about the textbook, and one of the things that bothers me about Chapter 2 is that they introduce amino acid-base chemistry. This is not an easy topic, and therefore I feel compelled to also introduce it, though I am going to take a different tact with it. Your book walks you through glycine and aspartic acid. I am going to walk you through glutamic acid in a somewhat different style, in hopes that if you are struggling with the book, then my lecture will make sense, and perhaps vice versa. So we are going to consider the amino acid glutamic acid, and we are going to think about it at various pH values. This first species of glutamic acid is a fully protonated form, which would exist at pH 1 or some extremely acidic pH. If we begin to add sodium hydroxide as a way of decreasing the acidity, the first acidic hydrogen that would be titrated would be the carboxylic acid group, which has a pK value of 2.19. After all of those protons have been removed from the molecule, if additional base is added, the next acidic hydrogen that would be attacked is the R group, which has a pK value of 4.25. Adding additional base will cause the protonated amino group to become deprotonated, as its pK value is 9.67. We will call these four possible structures A, B, C, and D. One of the things that the book introduces that I would not have until later is the concept of isoelectric pH, PI. PI is defined as the pH at which a molecule has no net charge. So to determine the PI value, we have to think about what the net charges are. With structure A, I see one positive charge and no negative charges. So the net charge is a +1. Structure B has one positive charge and one negative charge for a net charge of 0. Structure C has two negative charges and one positive charge for a charge of -1. Finally, structure D has two negative charges and no positive charges for a net charge of -2. The isoelectric pH is always determined by adding the pK values on either side of the 0 net charge, which in this case is going to be 4.25 and 2.19. Those values are added together and divided by 2 to yield the isoelectric pH of 3.22. A similar process can be gone through for the other two pK values of 4.25 and 9.67, yielding a value of 6.96. Though this is not an isoelectric pH, it does not have a special name like that. On this graph, what I am showing is a titration curve of glutamic acid. I have indicated with red dots 5 different points. It should be noticed that the first, third, and fifth points from left to right correspond approximately to 2.19, 4.25, and 9.67. These are the pK values for the different acidic hydrogens. The second point should correspond to the isoelectric pH, which we calculated at 3.22. The experimental value looks like it may be slightly higher than that. We also calculated a value of 6.96. It should be noted that the red dot on the vertical inflection looks to be at about pH 7. The other thing to point out about this chapter is section 2.5, which contains a word that I expect would be mispronounced by a number of students being initiated into biochemistry. This word is not pronounced macroions, but macroions. Figure 2.24 is a magnificent figure showing how significantly the characteristics of a protein can change when being placed in different environments. And importantly, an experimental fact is that the isoelectric pH solubility is at its lowest. All of you have probably experienced this without realizing what happened on the molecular level. You went to the refrigerator for a glass of milk, poured yourself a glass, took a nice big drink, and spit it out, hopefully into the sink. After tasting the acidity, you would have noticed, more closely examined that jug of milk and noticed that there was curdled white stuff, also known as cottage cheese, at the bottom of the carton. This is a classic example demonstrating the low solubility of macroions at their isoelectric pH. The last thing to point out about this is something I have alluded to which is osmolarity. Having an incorrect ionic strength, too high of an ionic strength, will cause molecules, whether large or small, to be more shielded from each other, and figure 2.25 is a nice example of this. To introduce some experimental information into the lecture, a very commonly used buffer in biochemistry is referred to as PBS, phosphate buffered saline, which is composed of 50 millimolar phosphate at pH 7.4 and containing 154 millimolar sodium chloride. This is an isotonic solution, meaning that it has the same osmotic strength as blood and interstitial fluid, but a different ionic composition. If one desires to have a more physiological solution, one might use KRB, Krebs-Ringer buffer, which every medical person should recognize as Ringer's solution. This is more physiological in that there is less sodium chloride, which is compensated for by the presence of potassium chloride, calcium ion, and glucose.